Today, we start our last topic for the semester, which is game theory. Game theory is a branch of mathematics that has very broad applications across a considerable number of different areas of study. This week, we're going to look at a particular kind of game called zero-sum games. Now, the general context here is that two players are playing against each other, but critically, they're playing simultaneously. So they're not playing the kind of games that you play in chess. They're playing without knowledge of how the other person is going to play. And the zero-sum games are games simply in which whatever one player wins, the other player loses. And to describe such a game, we have a payoff matrix, which describes the wins that one player will receive depending upon the moves that they make and the moves that their opponent makes. So we assume here that we have two players, player 1 and player 2, and player 1's gains are given in the matrix. For instance, consider a game of paper, scissors, rock. And the moves here are paper, scissors, or rock. And let's say that in each game that one plays, the winner gets $1 and the loser loses $1. So here is the payoff matrix. If player 1 plays paper and player 2 plays rock, player 1 wins $1. On the other hand, if player 2 plays scissors and player 1 plays paper, player 2 wins $1 and player 1 loses $1. If they both play paper, there's neither a win nor a loss to either player. So for any kind of game like this, you can set up the payoff matrix, and then we work with this matrix to obtain the best possible move for the players. In this particular game, the game is fair in that the winnings for one player are the same as the winnings for the other. We don't necessarily have to restrict ourselves to such games. We'll consider games in which the possible moves for one player might be different to the possible moves for the other, and that payoffs could be different as well. It doesn't make a big difference to the theory. So we'll consider games which are unfair in a certain sense. Now, the key notion in this whole theory is the notion of a mixed strategy. The point is that you can't just choose what the best single move is, and play that move repeatedly. For instance, in paper, scissors, rock. If your favourite move happened to be paper, for instance, and you kept playing paper, paper 2 would realise this and simply adjust their strategy and beat you every time. So in paper, scissors, rocks, and in most of these kind of games, you need to play a mixed strategy. That is, your best way to play is to play the different possible moves with different probabilities. And the idea is to choose the probabilities so that you will get the greatest gain. Now, if you play long enough, your opponent will notice what probabilities you're playing at, and they will adjust their probabilities as well. So the idea is you want to find the best choice of probabilities, assuming that you're playing against an intelligent player who plays as best as they can. So the problem is, how do the players choose their probabilities in order to maximize their payouts? And we're going to formalize this as a mathematical problem. And let's assume that there are n possible moves for player 1 and m possible moves for player 2, and let the probabilities that we choose for player 1 be denoted P1 to Pn, and for player 2 Q1 to Qm. And of course, the probabilities each have to sum to 1. Now, player 1 chooses their probabilities and player 2 chooses their probabilities, and then if you use the expected value formula that we looked at back in week 7, you see that the expected average payoff for player 1 will be the P vector, which is the vector of probabilities for player 1, times the payoff matrix A, times the vector Q, which are the probabilities for player 2. And player 1 wants to maximize this payoff. The problem for player 1, therefore, is player 2 will try to choose Q as to minimize this payoff to player 1, and player 1 wants to maximize what they can get even if player 2 plays intelligently. So if player 2 plays intelligently, they will minimize PAQ transpose by varying Q. And then player 1 wants to maximize the minimum by varying P. This is called a maxi-min problem, and it's a famous problem in mathematics. A maxi-min problem. You want to maximize the minimum of a certain expression. And the trick is to turn this into a linear programming problem. It's very clever. The idea is to introduce a function phi of p, which is the minimum over q of PAQ transpose. So here, in the right-hand side here, the p is temporarily fixed and q is chosen so as to minimize PAQ transpose. And that number then is the value of phi p. Now, since phi p is the minimum over all possible choices of q, we have that phi p is less than or equal to PAQ transpose for all possible values of q. In particular, if we look at the q values which corresponds to the pure states, then we get certain inequalities. Now the pure states are the states where you just play one particular move every time. So one move has probability 1 and all the other possible moves have probability 0. And if you substitute in the different possible pure states for Q, you'll get M inequalities. The first inequality corresponds to the first possible move for player 2, and then the last one is the last possible move. So we've got a bunch of inequalities, and they look really interesting, but they're not quite yet in the form of a linear programming problem. And the trick is to introduce a new variable xi, which is probability pi, normalized by dividing by 5p. And then the inequalities we have here can now be written in this form. And now these inequalities really are linear here. The problem before was we really didn't know anything about the function phi, particularly we didn't know whether it was linear or not. But now we've got a linear set of inequalities. So here is our linear set of inequalities written in matrix form, and our problem is to maximize phi of p. But you notice that 1 on phi of p is, well, 1 is p1 up to pn divided by phi p, and so this is p on phi p all the way up to pn on phi p, and so this is x1 up to xn. So maximizing phi p is the same as minimizing 1 on phi p. So what we want to do is minimize the sum of the x's. So this is our linear programming problem. Minimize the sum of the x's subject to the inequalities that we have. And you'll notice, of course, that here the inequalities are all greater than or equal to 1. And so in order to solve this problem, we would, if we left it like this, we'd need to introduce artificial variables. So it's definitely better to solve the dual problem. The dual problem will be maximize a certain sum subject to a particular inequality where, again, the C vector here will be a vector of 1s. 1s because the coefficients here are all 1s. Once we solve this and determine the x's, then we get the PI, the probabilities we're really interested in. They are given by xi over the sum of the x's. And that just comes directly from the definition. We know that xi was pi on phi p, and here we have 1 on phi p is x1 up to xn. Okay, now that's the general process. It's straightforward. Occasionally it can go wrong, and it can go wrong if phi turns out to be 0. You notice, regularly here we're dividing by phi p. If phi happened to be 0, we'd be dividing by 0 and the whole thing would just blow up. So you can occasionally get into trouble, and the idea instead is to, before you start, is just add a number to all the entries in the matrix, in the payoff matrix. And the thing to do is to add a number so that all the entries are non-negative. And the way to do this is just pick the biggest negative entry in the matrix and add that positive number to everything, making that negative entry 0. You can actually still get into rare occasions, phi can still be 0. But this is definitely a good way to start, and this process also guarantees you'll have at least 1 0 in the matrix, which is useful when you do the calculation. So here's the procedure. Write down the payoff matrix, add a constant to make sure none of the entries are negative. Write down the initial tableau. The right hand side will be a column of 1s. And the entries in the bottom rows in the non-slack variable columns are all -1s. You solve using the simplex method. That gives you the solution, and the dual solution is the one you want. It's the x's. Then you normalize to get the probability vector. The normalized version of the solution to the original problem is the solution for player 2. And the expected average payoff then is PAQ transpose. There is a really easy check for this, incidentally, and that is to take the reciprocal of the entry in the bottom right hand corner of the final tableau and then subtract the number you originally added to the matrix back in step 2, and this should be this should be your answer for PAQ transpose. Now, this is a really useful check. You should use it, and in fact, you may be required to employ this check.